Hello guys, how are you doing? Welcome back to Noble Episode Designer. I'm your host as usual, your instructor Abjoin Babatunde Bukola for this channel, Noble Episode Designer. Today what we are doing the topic is how to use calculator block in Aspen Plus, and it's just like from the series that we have been doing, Aspen Plus series, it's just like the basics of calculator block here in Aspen Plus. So we're going to be using the simulation that we have from our previous video on how to do your first simulation in Aspen Plus. So we are going to be adding some calculator in order to do some advanced analysis on the simulation, you understand. So in a nutshell, a calculator is just like your normal what it does what your normal calculator do. You understand? It helps you to calculate your flow sheet and insert some calculation code or statements in your simulation compilation. You understand? You can even, instead of using Fortran, you can even use an Excel flow sheet or Excel equation function. You understand? Just relationship between two cells in a cell. You understand? You can use it in your simulation through a calculator block. So before we go deeper in what a calculator block is, so I would like to do a little preamble, like a reminder on the simulation that we are going to work with today. It's just like a dryer simulation, you understand, where we have a wet cold drying and combustion. You understand? Of course, the coal is being dried to water content that we specify, which can be 10. You understand that because the coal contains some water content, such as the water content of the coal is feed coal is 25 weight percent, so it's going to be dried to 10 weight percent before it's being burned in the algaes. And before that algaes, there is algae reactor, which helps decompose the coal, you understand, into elemental components such as hydrogen, nitrogen, carbon, you understand, before it's now being burned through Gibbs minimization process, you understand. So we model it as a chemical process, like reduction of the Gibbs free energy. When a reaction that has when reaction occur, you understand, the Gibbs free energy of the product reduces. So just like the burning of the coal, you understand. So the burning here is just typical here, and we have having 0.9 mole fraction of nitrogen, 0.2 mole fraction of oxygen, and it is 90,000. So this flow, you understand, 90,000 pounds per hour fluid can be very, to get the combustion of your flue gases, the amount of energy that is being generated, that is all your temperature, you understand, your solid, you understand. So and the if assuming you don't want all this sulfur oxide, you understand, or you want a typical support, as you can adjust any parameter. So that's the meaning why we do simulation. But generally what we're doing today is trying to automate the whole process here, and you don't want to make it manual, like all the variable, most of the thing is being specified, all the parameters, or all the parameters in the blocks are being specified. So we want to automate it here, and based on flowsheet value using a calculator block. So the first automation, let me show you the simulation again. So we stopped here in the last video. So this is the simulation. Like I said, everything is input by I'm the one that input all the parameters for this, or for the flow sheet. So I want to automate the parameter like this using a calculator box to input the parameters here. So they can add a calculator block, although we are going to be adding two calculator block, one for the drying reaction calculation yield. You understand? When I was doing the drying reaction, I had to do if you check the video, I did fractional conversion to be 0.15, although it's supposed to be 0.1667. You understand? That is the recurring fraction, but but right now your calculator is going to be the one that will be inputting the value here. You understand? What I'll just do is to make sure, so I'll be playing with little amount of variables. You understand? Then I can model the simulation faster. You understand? Check different kind of range of resources, and you understand operational condition of the process. You understand? So we are going to be adding a calculator here, and for the decomposition too, we are going to be adding a calculator, because the decomposition depends on all this that will depend on the proximate analysis and the moisture content here. Some is this hydrogen H2O water content. You understand? Water content is 10% after being dried. You understand? So that's why we're having yield of 0.1. So all these values also depend on the ultimate analysis. Then it is being normalized. You understand? So that you include the water content there. But so I'm going to be adding a calculator. So those are the two calculators that I'm going to be adding in the simulation today. So I'll go to, you can add a calculator by using the navigation pane here. So you go to the flow sheeting operation, because calculator is a flow sheeting block in Aspen Plus. So you see different kind of operation, the science spec, which is like a control the feedback control process. We are not doing that one today. So we're going to go to calculator, then you go to new calculator. To add the new calculator, you can adjust the ID the way you like, but I'm just going to be using this ID. So that will take great time, but if you are doing the simulation on your own, you can be changing the ID. So the next thing you do after you add the calculator is adding the variables that you need in your simulation. So that will take us back to my presentation. So this is the code drawing calculation that I did, because in the video I told you that I did back calculation. So there are just two calculations that involves, is a very simple material balance calculation. One is doing calculation of the moisture content in this block. Let me show you the flow sheet so you can see. So in this block, you understand the amount of water that comes in. Then you can see there is two inlets, you understand, and the amount of water that goes out. So water is not coming in the drying gas, nitrogen into zero. So is the moisture content of the coal, that is water that is coming in. So which is coal in multiplied by H2O. H2O is the, from our key here, percent moisture, you understand, divided by 100. Then in the wet coal, then that will be the water that is coming in. Then we have the water that is coming out, you understand, that is H2O out, percent moisture that was specified to be outlet. Then the conversion of the reaction, you understand. So this one is the coal, you understand, the coal material balance. So coal out, you understand, is going to be coal in. This one should be plus. So but this is basic chemical engineering. So once I add this to equation, I want to make my conversion subject of the formula. So that's just the making some conversion subject of the formula. So you have the H2O in minus H2O out, 100 minus H2O out. So this is the equation that I'm going to supply to the calculator. and it's going to be written in Fortran. You understand? So I'll just add the variables that is needed. You call them flowsheet variable because you import them from the flowsheet. You understand? So I'm going to add the first variable, which is H2O in. So let me close this one so that we can see it clearer. H2O. Okay, my number lock is on. 2O. Why is the normal log doing like this? In. So you have to be sure of the name so that you don't make any mistake. H2O in. The naming is very important in programming. Like identifier, the identifier for the variables, and you really don't want to make mistake. H2O out. Then we have, you can first new is to create another one. So we have conversion. Okay. So the next thing is now to link the variable with the references. You understand? That is to the flow sheet. So I'm going to link H2O by making it a component variable for my, oops, I didn't give the stream name. That's, if you're doing it, try and give your stream the stream name that is unique so that you are not confused. So our 5 is our wet code stream. So stream 5. This error can come at any time. So cool. So oops, proximate analysis. The element 1 is the moisture content. You understand? We have to fix carbon, volatile matter, and ash. So so this is for the first. So we have the second one is H2R is block variable here. This one is block variable because I want it to be inputs. You understand? It's your input from there automatic. So let me check the name of the block again. This is really wasting my time. Block 1. So block 1 is first block, then this component attribute value. So you pick the substream co and proximate analysis 1. So I'll check that block again just to be confirmed. I think that's the block. Okay, it's set here co proximate analysis 10. Okay, I think that's everything. Remain the conversion that I'll specify. You can see everything is actually linked on the flow sheet. Is now you can now see the information or signal line that I call it on the flow sheet. So we have the conversion for the reaction. So reaction 1, this should be the reaction ID. So I think it's reaction 1 in the flow sheet. Where's block 1? I'll read reaction 1. This is the reaction number. Yes. So we have reaction 1. So this one is done. So this one should be using import and export variables. So the next thing is define what import and export variable. Import variable is variables that you read the results, but you don't write the result to the simulation calculation. You understand? So export is the one that the calculator, after it has done its calculation, like here's our result, he's going to send it back to the simulation flowsheet calculation. You understand? So I'm just going to make this two, you understand, because I want to be reading them from the flowsheet. So this one now exporting the conversion back to the block 1. You understand? That is the drying conversion. You understand? So, and this sequence is just to tell the runner, you understand, the control panel runner, that is when it is going to execute the calculation block. You understand? So I want it to execute based on the import and export variable. That is when they are available here. So when all the import is available, or the hierarchy in the simulation. I will show you the hierarchy here. You used to list it. You can see from this. You can see this is the hierarchy of the simulation. Block 1 was sequential simulation. Then block 2 your sign. So it's start to solve block 1 variable first. Then it proceed to block 2, block 3, block 4, block 5. You get it. So that's it. So based on this, we have two import variables and one export variable, which is H2O in is and H2O out is import variable, while conversion is export variables. So I think this one is now done. The next thing is going to conversion. So like I said, you can use Fortran calculation or Excel calculation method. If you use Excel, it's going to create a Excel spreadsheet. You understand that it is you can find the relationship between each cell. You understand, then it's going to use those cells. So you plug each variable into one cell. You understand, and it's going to use those cells to do the calculation. So what we are using Fortran, but the only issue is just the code that we are using is this code. Conversion is going to be equal to H2O in, H2O out, then 100 minus H2O in. So you just copy, you start your copy at row 1 colon 7 because the preceding colon has a special value. They are special row. So if you put values in those rows, it's going to mean different thing. You start your statement in column 7 when you're writing in Fortran. You understand? So that's what I'm doing now. Okay, so I've copied the code. So this is the code that we are using for this place now. So the next thing is let me try and arrange this code. Export and import is even the same thing. It's just an arrangement or something. Everything should be an arrow that actually lead out to the export. So let me check. Once the calculation is done, so then need to become this conversion. Okay, so we do the second calculator. So last I added like the same thing I did for the first. You go to new. This one is now having the same name. So for this one, let's see the code decomposition calculation. So for this is just the calculation. So we have the moisture here, H2O, then there is going to be the water content. Water content is like the proximate analysis, the first element from the preceding stream, you understand, which is the dry cold stream. Then it will be a fraction of the, 0.1, 10 divided by 100 still give you 0.1, just like writing the same time. So the right now is just going to be automatic. So when the moisture content changes, the H2O, it also has to change, you understand, the calculation. So we have the ash, which depend on the ultimate analysis value divided by 100 like the moisture. But right now we have to normalize it with the 100 minus water divided by 100. This will be help you to normalize all these values, the ultimate analysis to 100 minus moisture content. You understand? Because moisture content is not part of ultimate analysis. Ultimate analysis is given in dry basis. You understand? So you have to make it in wet basis. So that's the meaning of all this batch equation that you have at the end. You understand? So I'm going to start working on this. So the variables that I'm going to be adding is small. You understand? So the first variable I'm going to add is H2O. So just make sure you have the name of the variable right, so it doesn't create error. So let me clean this one so it should be adding. So the next thing is ash. I'll be adding water later. So you click new. Oh, this one is fast. I don't want to. It's slow. I don't want to use slow variables. So we have the carbon. H2, hydrogen for hydrogen. N2 for nitrogen. Cl2 for chlorine. We have the sulfur. Then O2 for oxygen. So let me check again. So H2O, ash, carbon, H2, nitrogen, chlorine, sulfur, and oxygen. So the next is now adding the water. Yes, now those are the import variable. You can arrange it the way you like. It doesn't have to be like import first or export first. So this one is now the vector to hold the ultimate analysis vector, because I can't be referring to all the value one after the other. It will take time. So it will, so this one is import. So this one too is import. So the rest are export. So okay, since I've done that one, okay. So the only thing now is to referring to those variables. So I'm going to start with HO first. So HO is component. Okay, it's block variable. What's the name of the block? Block 3. Let's see 2. Let's see 2. Let me close some of these forms so that we can see clearly. I'll close some of them. Some of them we are not being seen everything. We can't close everything. All these forms that we have opened since the beginning of this course. So we have block 3, if I remember. So we have the mass heat for hydrogen. There's hydrogen mix substance. So ash, pick ash, the same, follow the same process. Block 3, mass heat for ash, not conventional substrate. Then we have the carbon. Carbon is, remember, carbon is conventionally inert solid. So you have to pick that one too. So we have the block 3, mass heat. Carbon is C in the component list when we defined it in the component list. So we have the H2O or hydrogen, sorry, oops, mass block variable, mass heat, H2 mix H2O. Oh, made a mistake. This should be H2O. As I gave me here. So we have the block variable, block 3, mass heat, nitrogen mix. We have the chlorine, block variable, block 3, max heat, Cl2 mix. So you do for the remaining elements, you understand. So I skipped so that you make the page. The next thing I just want to check if I make any mistake, because there's going to be definition. So you just check from this place. So you have block 3 here, mass heat, MRC, the components, H2O, ash, carbon, C is carbon, hydrogen, nitrogen, chlorine, sulfur, okay, oxygen. Yeah, this one is mixed, not conventional. Conventional in our solid, then mixed matrix. So everything is fine. So you do for the water, which is the, you understand, this one is stream variable component. Okay, we have, oops, I really don't know the name of the stream. It's supposed to be glycol in your own simulation when you give it your stream name. So this one is stream 3 here. So stream 3. So we have the co-optional first element. So it's going to import that. So we have the ultimate analysis from there too. So this one is component vector. So string 3 cool. So utana, that's ultimate analysis. So let me check the name again. String 3. Okay. So this one too, you can put it there. Okay. Reduce this. Okay, this is the second calculator now. So ultimate analysis utana. Okay. The next thing is, let me check this one too if I'm right. So component stream 3 substream non conventional co-attribute proximate element 1. So this one is component vector non conventional stream 3 co-attribute utana. Okay, good. So last thing is now writing the code. Yes, and so just write this code there, like H2 is equal to this, so like mathematics equation, yes, but following the Fortran syntax, you understand, so not from the first. So I'm going to do that now, copy it up. So okay, make sure it's starting from, okay, so this one is, let me check, okay, so we have this. So these are our code, and you can see input change, that is everything, all the required form has been filled and all the needed inputs has been specified. So we can run and check our simulation like that. So let's run. So I'm trying to start again by resetting my simulation so that it purge all the result out. So you go to control panel, you see run. So you see the sequence there. So let me run. So it's processing the input specification. So the simulation has been done. So it's saying there are two warning in the simulation. So let me see the warning. There is our normal warning, the RU warning. I think I can only see the RU. Okay, this one is saying warning during flowsheet analysis conversion one sequence to control. It's saying this may cause misleading results. Maybe it's because as using the product, you send to calculate the feed CL stream conversion for calculator 1. Okay, let's just see what happened. Watch run fine. Okay, it's now giving me the right answer at 0.176667. So just the one in there in the flow sheet topology. So you can see now, so this one too is also there working fine. You see the value that I'm specified is not changing because I've already done the back calculation, you understand. So it's not doing it for me now, you understand. So this is the input that is saying import variable. So this is the result that is read into the simulation. So okay, so we are going to make some changes in the simulation and see the effect of our new calculation or our new calculator, what is block is doing on the simulation. So I'm going to be changing the specified, okay, where is this component attribute, outlet component attribute to 20 first and see the simulation effect. Okay, this one is not even showing me the error one is at all, so you can see. So you can see this one has changed from 0.15 to 0.00. This is what it's now reading. Although this is what I specify in the flow sheet, you understand, but this is what you send to the flow sheet calculation, you understand. It will ignore that the one that I specify, you understand. So we have 20. So this one's coming out, the moisture content that's coming out of the drying reaction, 20. So this is the reaction, you understand. So you can see our values have been changed. This one is now 20, isn't it? Yield of water that is there, 0.2, yes, and 20%, which percent. So we have the fraction of chlorine that will be in the heat, you understand. The ultimate analysis was also changed, you understand. So it's help us to automate. So then I'll change it back to much lower and see the effect now. So I'll change this one to 5. Said to check the effect. So this one is giving us error. This is sure. Warning. I mean, that's error. I don't want error. I want warning. Warning can still be managed. So this one is now 5. You understand, from 25 to 5. So the moisture has been reduced much. So from this you can check different kind of thing that occur in the whole process. You understand, the temperature that is coming out of the reaction. It's going to be changing as the temperature. So you don't need to be worried about, you understand, changing the reaction rate again. You understand, you don't need to be worried about changing the conversion again. Yes, and the calculator will take care of that. So that's what we use calculator to do in Aspen Plus. So you can see the temperature here is 2877. So if I change it to another value, let me change it to 2877. So let me change this one, do that one last. So I'll make it to be 0.5 moisture content, 2875775. Okay, done. So where's my stream? Okay, you can see the stream temperature has changed, 273043. Yes, and so we can check the effect of the temperature and all the stream after temperature from the combustion process. So I think with this, that will be the end of our videos on the basic of solid simulation in Aspen Plus. So watch out and stay tuned to this channel. Once again, I'll try Babatunde Kukola. Thank you all.